Good morning, everyone. It's my pleasure to introduce Vinh. Vinh obtained his bachelor degree from our department in 2020. And before that, he actually spent 1 year in my lab working on the research, and we're very happy that we're able to entertain him. So he decided to stay and continue his Ph.D. He joined the lab in 2020 and working on several projects. One of them is on this nano engineering of membranes, which is quite challenging because it's always tricky to control the material at a nano scale, because what you do today could be very different from what you have done 3 months ago, just because equipment broken down, you've done some repair. So Vinh was really trying to go through that process. One fact about Vinh is he's active cyclist. Right? He actually told me he did a cycling 50, 80 miles a week. He told me the difference between biking and cycling. It was quite interesting. And he enjoyed, paddling and then different scenery views. And I think he applied that methodology in the research. He got to take a lots of data, and then trying to, find some observation through this data mass. Right. With that, I'll let Vinh share his journey here.
Thank you, Dr. Lin, for the very kind introductions. And also thank you to the department for this amazing opportunity. It's actually been my dreams to give this student lecture at the Symposium. So I want to start off with some hydrogen economies. So as we may know, hydrogen is a very important gas. It can be used as raw material for a lot of chemical and material synthesis. It can be used for synthesizing fertilizer, which is very important for food, right? And hydrogen can also be used as a clean source of energy, which can be used to electrify cars and electrify homes. And ultimately, we want to produce hydrogen using what is called electrolysis, which is breaking down of water, where the electricity can be applied, produced, using the renewable source of energy, such as like solar or a wind turbine here. Unfortunately, this ultimate figure is not quite feasible just yet, and that the production of hydrogen still heavily depends on the reforming of coal and methane. So what's shown here is the schematic for the coal and methane reforming, where coal and methane can be gasified with water and oxygen to produce syngas, which is hydrogen and CO, which can be further shifted with water to produce more hydrogen gas. And before this hydrogen can be utilized, you need a CO2 separation process here to purify the products and to capture the CO2. So according to the recent report from the National Energy Technology Laboratory, the separation process can take up to 20% cost of the hydrogen production. And the energy consumption is roughly 20% of the energy if all of this hydrogen was to be converted into the energy. So it's very, very cost and energy insufficient. So we think to ourselves as a membrane scientist, what about membrane? Can membrane really help us with this application or not? So before I continue with my technical content, I want to give you a brief outline of this presentation. So first, I'll discuss how silicon material can be very effective for this separation, as well as some challenges facing silicon membrane that hindering the industrial application of the silicon material. As such, I would propose this new material that's called polyorgano or silica or POSI membranes that exhibit separation performance similar to that of a silica, but can be prepared within just 3 or 5 minutes of oxygen plasma treatment. I will also discuss how the polymer structure, polymer precursor, and the fabrication process, the parameter of the oxygen plasma, can help us fine-tune the structure of the POSI and enhancing the separation performance. And lastly, I will discuss how the atomic layer deposition can help us, doing the final polishing of the membrane for the hydrogen over CO2 separation. So what is membrane, you may ask? So membrane is a semi-permeable material that allows a passage of one gas while rejecting the passage of another. So this technology does not have any phase changes, similar to that of the sorption, have some phase changes, whereas for membrane, it doesn't have any phase change during this process, and thus the energy efficiency of this technology is very, very high. In addition, there's no hazardous chemical involved in this technology, which is a plus. So the working mechanism for membrane can be described by solution diffusion, which say that the gas permeability is a product of solubility and diffusivity, which means that the gas will first dissolve in the membrane matrix and then diffuses through the membrane material. And the separation property of the membrane is just the ratio between the two gas permeability. And then you can break it down into solubility selectivity and diffusivity selectivity. So these two selectivities are often guided by the property of the gas itself. So if we look at here for the hydrogen and CO2, hydrogen has smaller critical temperature than that of the CO2, meaning that CO2 is more easier to dissolve into the material, which means that for membrane application, the membrane often favoring the absorption of the CO2, or solubility selectivity of hydrogen over CO2 is less than 1. Whereas if we look at the critical temperature, kinetic diameter, we say that the hydrogen is smaller than that of the CO2, indicating that the hydrogen is more likely to diffuse through the material than that of the CO2. So the diffusivity selectivity is strongly favoring the separation of hydrogen over CO2. In other words, if we want to make a membrane work for this application, we want to develop a membrane material that exploit on this diffusivity differences. Or we have to make a membrane that have the pore size that is larger than hydrogen, but smaller than that of the CO2. However, there has been a lot of reports on the trade-off between the selectivity of the membrane and the flux to the material, as shown here as an upper bound. So what it showed is that the membrane with higher gas permeance will exhibit smaller gas selectivity, and the membrane exhibit higher gas selectivity will exhibit smaller gas permeance. For example, for the PPO here, material, I don't know if you can see it, but the gas permeance around 50 GBU with the selectivity of roughly 2, less than 2. Whereas for the PSF, it's exhibit a selectivity around 3, but the gas permeance is only 10. And also shown on this plot is the target performance here. So this target performance is the performance that membrane need to achieve in order to have this separation process be economical. And as you can see, there's such a big gap between the commercial polymer and this target performance. Very interestingly, in 1998, a group of scientists from Netherlands, they discovered that silicon material can have such a tremendous separation performance for hydrogen and CO2. And this is because of the very unique pore structure of the silica that has the pore size larger than hydrogen and smaller than the CO2, leading to a very rapid transport of the hydrogen with a very precise separation from hydrogen and CO2. So what's shown here is the cross-sectional SEM image of the silica membrane. And you can see that the silica material is roughly like 30 nanometer on top of 2 layers of gamma alumina. But it's been 26 years since this material has been developed, and we haven't seen any commercial of these membrane yet. And this is because the fabrication of the silica membrane requires a prolonged period of calcination at 600 degrees C and very expensive inorganic support. And this inorganic support, you cannot just use it as you got it. You still have to do conditioning, which is to make the surface smoother, pore size smaller. That's why you see a second gamma alumina here. And this conditioning incorporated with the calcination, it's a very energy and labor-intensive process to make silicon membrane. So what I showed here is a separation performance of what is called a polysiloxane, or just a silicon rubber. It's a very, very inexpensive material that exists in most of our daily life material, such as contact lenses. It can exist in the garden hose, that's why it's very flexible, and also in the sealant of your aquarium. So the polysiloxane is a bit very high gas permeance, but very, very weak hydrogen over CO2 selectivity. And what I want to show you today is that we can convert this polysiloxane material into something called polyorganosilica that exhibits separation performance similar to that of the silica material, but with just only 3 to 5 minutes of oxygen plasma treatment. And what is oxygen plasma treatment? So oxygen plasma is just the fourth state of matter, and this can be generated by passing an oxygen gas through this conductive coil, and this conductive coil would flip the magnetic field very rapidly, stripping away the electrons of the neutral gases, ionizing the gas. And these electrons can also collide with the neutral species to prepare more ions. And we can attract all of this oxygen plasma toward our membrane surface by applying a electrical voltage bias, which is controlled by what is called a reactive ion etching radio frequency source here. And everything is very well controlled within a chamber. So that is plasma treatment. And here's the construction of our membranes. So we start off with some polymeric support for us, and then we coat this polysiloxane material on it. And the polysiloxane material that we do in this study is the polydimethylsiloxane called hydroxymethylsiloxane. And then we expose it to the oxygen plasma between 90 to 180 seconds to convert the skin layer into a POSI structure. So what's showed here is the SEM cross-sectional image of our membrane. You can see some porous PSF support here. And you can see the combined thickness of the POSI and the polysiloxane is roughly 400 nanometers. And you can also notice that we cannot distinguish between the two layers, between POSI and polysiloxane. And this is because the effective thickness for the oxygen plasma treatment is very, very thin. And I will show you that later on. So to confirm the POSI formation, what we did is the XPS analysis. So what's showed here is the atomic ratio, oxygen over silicon atomic ratio, and carbon over silicon atomic ratio of the polysiloxane and of the POSI. So the polysiloxane exhibit a 1.2 oxygen over silicon content, whereas for the carbon over silicon content, it's 2.09. After the plasma treatment, we see that the oxygen contents increased to 2, and the carbon over silicon contents decreased to 0.75. And this reduction and increase in the oxygen over silicon contents can be described as follows. So when you have a polysiloxane, you expose it to oxygen plasma. The oxygen plasma can come in and cleave the organic groups on these polysiloxane, creating an active site on the silicon. And if you have two adjacent silicon with a bunch of ions flowing around, you're going to form a siloxane linkage. And this simultaneous reaction can help us convert a polysiloxane material, a rubbery material, into a silica-like rigid structure called here, as shown here. And it's also worth noticing that the theoretical value oxygen over silicon content for silica is roughly 2 because it's SiO2. And what we have here for POSI is 2.18, very similar to that of a silica. So in our previous study, we also probed the oxygen over silicon content as a function of depth, or the etching depth of 0, meaning that the surface of the material. And this is of the POSI material prepared at 15, 120, and 360 seconds. We can see that starting from the surface, the oxygen over silicon content from 2 can gradually decrease down to roughly 1 within the first 20 nanometer of the etching, like 20 nanometer from the surface. And if we consider that 1.5 oxygen over silicon ratio as an indicator for silica formation, then these membranes actually have the thickness of less than 10 nanometer, truly thin. So we also did some surface chemistry for the POSI membrane using the XPS peak deconvolutions. So what's showed here is the Si2P and the C1S peak deconvolution for the polysiloxane and the POSI. So for the polysiloxane, we have two distinguished peak here, the Si connected to 2 oxygen and 3 oxygen groups. But after the oxygen plasma treatment, we see that these two peaks rapidly depleting with the immersion of the SiO4. And this Si connected to 4 oxygen group immersion, it strongly indicating very consistent with the silica formation that we observed earlier. On the other hand, for the C1S peak deconvolution, we see that the CH peak depleted with the immersion of the CO peak, indicating the oxygen addition into our POSI structure. So in order to understand the physical structure of the POSI on the surface, what we did was the grazing incident wide-angle X-ray, or GWAX, and this was done by Brookhaven National Lab from Dr. Nam's group. And it's very similar to the XRD technique that you often use in any material synthesis, material characterization. But this one instead, you shine an X-ray at an incident angle, and that will be very surface sensitive, just surface sensitive. And for this study, we did incident angle of 0.05, which translates to roughly 5.2 nanometers on the surface of the material. So what's shown here is the GWAX data for the polysiloxane. We see that there's a peak around here, and this can be attributed to the change folding, the ribbon-like folding of the PDMS contribution of the polysiloxane. On the other hand, for the GWAX, for the POSI, we see virtually no peak on the GWAX signal. And this indicating that the material is extremely amorphous, which is, again, very consistent with the formation of amorphous silica on top of the polysiloxane. So we also studied the effect of polymer precursor on the POSI formation. So we look at 2 generations of POSI. So the Gen 1 is prepared by PDMS, and Gen 2 is prepared by this copolymer polymer here. And the difference between the two is just that the Gen 2 have this extra silanol groups here. And as we can see from the XPS, the Gen 1 exhibit an oxygen over silicon, and the Si contribution, Si connected to full oxygen contribution, lower than that of the PureSi Gen 2. And this indicating the addition of hydroxyl groups in our polymer precursor can help us enhance the formation of the silica after the plasma treatment. What's showed here is the gas transport property of the PureSi Gen 1 and Gen 2 permeance and selectivity here. So as you can see, increasing in the exposure time, the gas permeance rapidly decreases, indicating the tightening of the polysiloxane structure. And this tightening of the polysiloxane structure leads to a very rapid enhancement in the gas selectivity. For example, the PureSi Gen 1 can exhibit a selectivity up to 80. So even though we have some very, very exciting result, when we look at the performance of this material on the performance plot, we see that these Gen 2 and Gen 1, they fall a little bit short from the target performance. So there's still a lot of work to do to boost this performance. And as I showed earlier from this schematic, there's actually a lot of variable in this plasma treatment process. And if these variables can effectively control the ionization of the gas, then we think that it should also help us control the structure of the PureSi and the gas transport property also. So what's showed here is the effect of ICP power, or the power input into ionization of the gas, onto the PureSi gas permeance and hydrogen over CO2 selectivity. We see that with increasing in the ICP power, the gas selectivity rapidly increases, whereas for the hydrogen permeance, it slightly decreases. When we look at the XPS, we see that the membrane prepared it at 50 watts exhibit a carbon over silicon contents higher than that of the 200, and the oxygen over silicon contents lower than that of the 200 watts PureSi. And this indicating that the membrane prepared at higher ICP exhibit higher silica contents. And this is very consistent with the additional energy input into the system to ionizing the gas, right? So the more ions you have, the higher efficiency of your plasma treatment, leading to a higher silica content with stronger gas separation property. Very interestingly, when we look at the effect of chamber pressure, we see that with increasing in the chamber pressure, the gas selectivity actually decreases, whereas for the gas permeance increases. And when we look at the XPS analysis of these membranes, we see that there is not much of a change in the chemical composition as well as chemical structure of these PureSi material prepared at 50 or 500 millitorr. We have some hypotheses that at higher pressure, the gas are closer to one another, so the kinetic energy, so they can collide together, reducing the kinetic energy of the ions, leading to a thinner PureSi formation. But because of this PureSi membrane is such thin nanostructure in the first place, it's very, very hard for us to quantify this hypothesis. So we also did study on the effect of exposure time here, the oxygen flow rate, the RAE power, and also the ICP RAE coupling effects. So you need not to worry about the detail of these plots. I just wanted to summarize it here to show you that we actually look into the effect of other parameters. And this is because we want to develop an optimized oxygen plasma treatment for our PureSi membrane. So what I showed here is the separation performance of our PureSi membrane comparing to other state-of-the-art material and comparing to silica membrane. It is actually very superior to other polymeric material. It is slightly lower than that of the silica, but most importantly, it's within the target region that we try to aim for. And to further illustrate the promising aspect of the PureSi membrane, we also did some mixed gas study, which is we changing the feed concentration. And we see that the gas permeance of the membrane is very, very stable, as well as the gas selectivity. And this is very, very desirable feature of the membrane because in industrial application, you cannot expect the feed to be at a constant concentration, right? We also trying to look into the long-term stability of the membrane. So this is the gas permeance and gas selectivity. So we see that in dry condition, the membrane is quite stable. But when we expose it to the water, so we introduce a little bit of water into the feed, we see that the gas selectivity actually depleted. And when we switch back to the dry condition, it doesn't recover. And when we're further increasing in the water content of the feed, the gas selectivity further decreases. And this is very, very disappointing when we look at it. I mean, discouraging, not disappointing. But it's very well documented in the literature. And this behavior can be explained by this reaction right here, where the polysiloxane can be hydrolyzed to produce these mobile solenoid groups. And these mobile solenoid groups at high temperature can recondense with one another to reform this siloxane here. And this simultaneous hydrolysis and condensation of the siloxane can rearrange the silica structure, leading to a loss in gas permeance and gas selectivity. And this really pushes us to look into the literature and trying to find a way to stabilize the material, which brings me to the next part of this presentation, which is to polishing, fine-tuning the POSI with atomic layer deposition. And atomic layer deposition is a cyclic process where you have a substrate with a hydroxyl groups on it. You can expose it to the TMA, which is a alumina precursor. And this TMA can interact with the hydroxyl groups to craft the alumina on top like this. And these unreacted methyl groups can be exposed to water to, again, make hydroxide. And then you can also recycle this whole process, again, to atomically deposit the alumina oxide on top of your substrate or your material. So it's roughly 0.8 angstrom per cycle at 80 degrees C for this technique. And this technique is actually a very scalable technique. There's a 1.7 billion market cap for this technology used in electronics, semiconductors, medical device, and others, right? And this technology can actually be used for flat sheet material. As shown here from Spark Nano, you can actually use ALD in a roll-to-roll fashion, which is very desirable for our membrane fabrication. So what I showed here is the cross-sectional and the surface of our POSI with 3 cycles of ALD. And as expected, we don't see any different in the structure because 3 cycles is only 2.4 angstrom of alumina oxide deposition. Similarly, when we look at the XPS, the material is still very, very smooth. It's very hard to distinguish between before and after the alumina oxide deposition. But very interestingly, when we look at the gas temperature and transport property, we see that with the increasing in the aluminum cycle, and I should notice here, it's only a few cycles, up to 5 cycles here, we see that the gas permeance for hydrogen is slightly decreases, whereas for the CO2, CH4, and nitrogen, it's rapidly decreasing with the increasing in the ALD cycle. And this leads to a very sharp improvement in the separation of the membranes. For example, the hydrogen over CO2 can reach up to 380, which is tremendous for this application here. We're also trying to look into the stability of the membrane, similar to that of the POSI. We see that the membrane exhibits very constant, very stable performance in different gas mixture. And very, very excitingly, when we look at the long-term stability and wet condition, we see that the performance of the membrane are quite stable. So we hypothesize that a TMA, it can go in and interact with these solenoid groups of the POSI, tightening the structure of the POSI while simultaneously stabilizing the structure. However, these are just our preliminary data, and there's still a lot of work to be done to confirm this hypothesis. So I hope that this presentation have showed you that the oxygen plasma treatment of polysiloxane can help us prepare a very robust membrane for hydrogen over CO2 separation in a very, scalable fashion. And also the scalable technologies such as ALD can help us polish this membrane, do the final polishing, enhancing the POSI separation performance and stability of the material. And here's the POSI in the performance curve. And with that, I'd like to thank Dr. Lin for his guidance and our collaborator, Dr. Hu, Dr. Zhu, and all the master and undergraduate students that I have the opportunity to work with, Liz, Almadine, Varun, Sai, as well as our collaborator, Dr. Louis Varade from the chemistry department, Dr. Nam from Brookhaven, as well as the clean room staff, the funding from the NSF and the DOE, and this amazing opportunity to give this lecture today, our Department of Chemical Engineering. Thank you.
I think we have time for just a couple of questions for Vinh.
Yes.
So when you, this stability thing was very fascinating. So now when you have your pore now has this alumina stuff in there, is it now blocking your hydrogen from moving through, or is it still where the hydrogen can fit through the remaining pores there?
So it's look like it's reducing a little bit from this is like without the ALD cycle, it's actually reducing a little bit,
Okay.
but it's still, yeah. Mhm. Yes.
Great work. On a related point, how do you envision the rigidity of this structure at the molecular level? Is it more like a polymer, or is it more like a zeolite, where it's, they're kind of fixed in space, or is it in between the two?
That's a very, very good question. I think it's more toward of not zeolite per se, because like zeolite is like a crystalline. We're thinking it's very rigid. It's a rigid structure, but it's very hard to say actually. But I think I envision it's gonna be just silica. But yeah.
Thank you.
Yeah. Yes.
In commercial methane production, of course, there's other materials. There's H2S, there could be particulates coming through, et cetera.
Mhm.
Is there any plans to test this with any of those other
Right.
possibilities?
Yes, that's an excellent point. So unfortunately, we don't have the H2S in our lab. It's like a little bit safety hazard kind of thing. But it's actually our plan to look into like commercialization of this membrane and try to look into the actual operation condition at industrial relevant condition. Yes.
So, look at your selectivity for hydrogen, nitrogen,
Mhm.
methane, pretty high already.
Yes.
So those nitrogen, methane below 0.4 nanometer, PMA is probably 0.5. I think PMA cannot get into the pores of this coating. It's probably modifying the surface.
Okay.
So I suggest maybe you can do some surface characterization to see how deep the aluminum is penetrating.
Yes. Yes, that's a good point too. So we actually have a plan to look into the surface characterization like you suggested. But yes, so yeah, it's an excellent point because like you're right, like TMA cannot get into the pore quite easily, like you said, because it's quite high already.
Very high hopes for the new XPS arriving in the next.
Right.